warm up how you use the first derivative and the second derivative to find your stationary inflection points. This is on page 22. So you can check if you're on the right track. So this level has been passed. Oh no, it hasn't. Because polar bears are on land. Good, 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 good. Fish are in water. Good, 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 bad. So you have to fix it. No, fish in water, polar bears on land, nobody on the people. Mm-hmm. And then there's different difficulties. So this is a junior level one. Let's go. How'd you do? 1, -31. So you have your local max, you have your local min. Another point you could find is your y-intercept really easily by plugging in 0 for x. And then it's just a matter of, can you take those things and put them onto your graph? One thing I would do on here is I'd label this one as y prime and this one as y double prime, so we know which ones are which. Is that a value that you were waiting for the solution to come up so you could write it down? Yeah, so as far as drawing the graph goes, going to have to estimate your scale on the y-axis a little bit. Notice that the x-intercepts are slightly red colored. If you want, you can always sit here. Then we'd have no problem. Everybody good on this one? Yes. You have another question that I took? Oh, okay. Good. You have it? The 2/3 one. Okay. I have an old set of notes that doesn't have that here. Okay. I'll just add it in. There we go. Oh, I know why we have this one. Because it's fun. Okay. So we start with our derivative, y prime, which will give us 2x to the negative 1/3 minus 1. Set that equal to 0. Are you okay if I change that to the cube root of x on the bottom? Okay. Minus 1. And solving this, multiply both sides by the cube root of x, cube both sides, and we get x is equal to 8. Also, and this is why this one is interesting, we also have a non-permissible value on our derivative that we did not have on our original function. So on our derivative, x can't equal 0, because then you would be dividing by 0. But our original function, x could be equal to 0. So this is going to be interesting. So this non-permissible value at x equals 0 tells us that no derivative exists when x is equal to 0. And we're going to find out when we get to the final graph. But as far as drawing your number line for your derivative, you have to put 8 on there. But most people forget or miss that you also have to put 0. So what happens? We plug in something less than 0, a negative number, okay, like negative 8. The cube root of negative 8 is negative 2. You can do cube roots of negatives. That's okay. And you get negative 1 minus 1, which is negative 2. This section is negative. Means your function is decreasing before 0. Plug in something between 0 and 8. Okay? For example, 1. This will be 1. 2 minus 1. This will be positive. So it's changing direction at 0. Even though 0 is not a stationary point. For a stationary point, it's only happen when the derivative is equal to 0. So it feels a little strange. We'll see what that does to our graph. And then after 8, if you plugged in something like 27, right, we would get 2/3 minus 1. It will be negative and decreasing again. So we could say that 8 comma, and if we plug it into the original equation, we'll get 4. Is that right? Cube root of 8 is 2. 2 squared is 4. 4 times 3 is 12. 12 minus 8 is 4. 8 comma 4 is a local max. We're not quite sure what 0 is. We know that something interesting happens at 0. And if we plug 0 back into our original equation, we get 0. 0 comma is a interesting point. I don't know if we can write that down yet, but we don't know what's really happening there. Okay? Second derivative. So we're going to take our first derivative, switch colors here, y double prime. We had 2x to the negative 1/3, so now we'll have negative 2/3 x to the negative 4/3, and that is it. Okay? This is equal to, I'll set it equal to 0. Sure. And I'll just change the format here, so it's negative 2 over 3 cube root of x to the 4. Okay? If you have a fraction equal to 0, the only way that fraction will ever equal 0 is if the numerator is equal to 0. So this has no solution. Does it have any non-permissible values? Yes. It does have a non-permissible value. X can't equal 0. Okay? So we draw our number line for our second derivative, and we put 0 on there. We check a value less than 0. Can you see that no matter what you plug in, the bottom's always positive, the top is always negative? So when we plug this in, this is going to be concave down. When we plug this in, this is going to be concave down. And now we have to go about graphing this. I'm going to put my graph right here. I'm going to zoom out so we can see all of our work at once. I'm going to label 8, 4. I'm going to label 0, 0. And initially, with those 2 points and this first graph, you might think that the graph looks like this. What's the problem with that? It's concave up in this section. So it has to disappear. When I make mistakes, it just automatically disappears. It's a nice new feature. It's like, can you imagine you're writing a test? You get to the end, you want to check it over, and it's like, why did I leave half of this blank? Because it automatically erases whenever you make a mistake. Okay. So how does this work? What does this graph look like? Because in order for this, if 0, 0, which sure looks like it should be a minimum in a regular curve, the only way that that would happen is if it was concave up. But to the left of 0, it's concave down. So it's got to be something like this. Does that fit that it's decreasing from left to right? Does it fit that it's concave down? And then in this section, it also has to be concave down. And so we get a graph with a cusp in it. Ooh, and also, could we solve, does it go through the x-axis again? It's a question that we'd have. Well, we could figure that out if we set y equal to 0. Can we solve that easily? We have, if you factor out an x, you would be left with correct? Could you solve this? Well, we got x equals 0. That's the one we already knew. On the other side, we would have 3 over the cube root of x is equal to 1. And so x has to be 27. And so you would have another x-intercept way over at 27. This is the little 3. Yeah. That's a cube root because it's negative 1/3, so the x would be to 1/3 on the bottom, and a 1/3 exponent is a cube root. Oh, good. Does anybody not have this question in their notes that got an old version of the notes? You all got, just I have the old version? I know, but I had some old ones, but I guess all my old ones had the nice question, new question added. Okay, we can go. to the next question, showing that x to the 4 does not have any inflection points. So you need two things for there to be an inflection point. You're going to need to find your second derivative, and it has to be equal to 0. Now, if we start finding our derivative here, and then our second derivative, we do have a place where the second derivative is equal to 0. But just because the second derivative is equal to 0 does not guarantee that that point is an inflection point. It also has to change concavity before and after. And so on this one, when you find that second derivative and you get 12x squared, no matter what you plug into 12x squared will always be positive. So it's concave up before 0 and concave down after 0. Concave up, thank you, after 0. And I don't know if you remember, but I said the other way that you can show an inflection point is at that value if the first derivative doesn't change sign, but our first derivative does change sign at 0. So how do we show that it does not have an inflection point? We'll need a statement here. Oh no, I know that's like way more letters than numbers. Not good for a math class. So it doesn't have an inflection point since the only value when the second derivative equals 0 is at x equals 0, but it's concave up before x equals 0 and concave up after x equals 0. So it doesn't change concavity and therefore is not an inflection point.